All right. Hello again, you guys. We're going to be talking about sex-linked today. So sex-linked traits. We want you guys to be able to calculate the probability of offspring having specific genotypes and phenotypes given parental genotypes. So that is something, the learning target is something that hasn't changed since we started doing the mono and dihybrid Punnett squares. Our learning objectives, we want you guys to be able to solve sex linkage Punnett squares using phenotype and genotype ratios. We want you guys to be able to express probabilities using phenotype and genotype ratios, and we want you guys to express probabilities using percents and fractions. So the only new learning objective is going to be the first, where we want you guys to be able to solve sex linkage Punnett squares using phenotype and genotype ratios. All right, so we're going to start off with just a couple of reminders of things that you guys already know, or at least hopefully already know. But if not, well, this is a good place to learn it and a good time too as well. So, genes are located on sex chromosomes. And sex-linked genes are going to be specifically the genes that are located on the sex chromosomes. Many species have specialized sex chromosomes. In humans, we call those the X and Y chromosomes. That would be our 23rd chromosome as well, but we always refer to that as our X and Y. And then in mammals, individuals with two X's are female, and individuals with one X and one Y are going to be male. Okay, and that can be seen right over here on our little cross. So this is just basically a cross showing you that every time a male and a female decide to have a baby, there's going to be a 50-50 chance of getting a boy or a girl. And another thing that I want you guys to know is that because a female only has one X, she can only pass on that X. Males have an X and a Y, so they can pass off an X or a Y chromosome. This means males choose the sex of the child. This isn't a choice that they can just make. They can't just decide to have a boy or a girl, but their sperm is going to be what decides it. Whether that sperm that fertilizes the egg is contains either an X or a Y chromosome. Okay. Now, the next thing I want to talk to you guys about is why are males more likely than females to have sex-linked disorders? Well, simple answer. Same way that we get to choose the sex, we only have one X chromosome. That is very important to sex-linked disorders. So because males only have one chromosome, or one X chromosome, we do not have the ability to we do not have the ability as males to use our Y chromosome because it does not contain the same genes that an X chromosome does. Okay, so when a female has two X's, one of those X chromosomes can have a sex-linked disorder, and she can be totally and utterly fine. She won't show any symptoms. She won't show any type of distress from that. However, a male only needs one X chromosome with that disorder on it in order to have that disorder, because males only have one X chromosome. So that is going to be the most important part of what we're talking about today, or one of the most important things that we talk about today is just knowing males only have one X chromosome, and that is why we are more likely than females to have sex-linked disorders. And just like a couple examples of sex-linked disorders that I'm talking about, there's types of hemophilia, and that is a disorder in which your blood doesn't clot correctly. And then another one is just red-green color blindness. And again, these are both going to be two disorders that are more common in men. Okay? Now, let's take a look at why that is. So, on the far left, we have the X chromosome. And then slightly to the right, we have the Y chromosome. Okay? So, one of the very first things that I'm sure you guys can notice is that the Y chromosome is much, much smaller than the X chromosome. Another thing that you should notice is that the Y chromosome has 5 genes on it, and the X chromosome has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. About 13 genes on it. So, the X chromosome has almost 3 times the number of genes present on it. So, sex-linked gene patterns of expression is different than autosomal genes, which is what we've been talking about up until now, is just autosomal genes. So when we talk about incomplete dominance, codominance, all those sorts of things, those are almost always going to be referring to the autosomal genes. Okay? X and Y chromosomes contain different genes, which is made very clear here in this image, where we see, again, 5 genes on the Y and 13 on the X. So that is what I really want you guys to take away from this image. It's just the fact that the reason why that males can't use the Y chromosome as a source of like replacing their X chromosome is because the X chromosome contains genes that are essential to life, and the Y chromosome, it does not. All the genes on the Y chromosome are just going to be for this male characteristics, and it's actually one of those genes it's the SRY gene, and that is what tells the fetus to start growing, like things like the external genitalia and those sorts of things. So I just wanted to show you guys that before we got too far into the sex linkage, and hopefully it makes a little bit more sense when we get that far into the notes. Okay, another thing that I want to talk about right away is carriers. So carriers are going to be an individual who carries a recessive or detrimental or unfunctional allele, and this causes harm. This can cause harm to the individual if it is if that is the only genotype present. The carrier itself is unaffected by the detrimental allele. However, this carrier can still pass it on in its gametes. So if we have a detrimental allele, like we do up here, so hemophilia is recessive to normal blood type. So in normal blood, you have clotting factors. In hemophilia, your clotting factors do not work properly. And then we are crossing a female right here who is a carrier for hemophilia with a male who has hemophilia. Okay? And now, another important note is that carriers will always be female in sex-linked disorders. You will never see a male carrier because males cannot be carriers. Males will either have the disorder or they won't. There is no in between because the Y gene is not big enough to contain both, or is not big enough to contain the allele for it. Okay? So here we go. We're crossing. We're going to get, for the first one, we get XH, and then the other X is going to have a big H on it. Then we are going to have an X with two small h, so X little h, X little h. We're going to have an X H Y, and then an X little h Y. So notice, these two individuals, hemophilia. This individual is going to be a carrier for hemophilia, and this individual is just going to be completely and totally normal. So the male, one of the males in this case is going to be totally normal. One of the males is going to have hemophilia. One of the females is going to have hemophilia. And one of the females is going to have or be a carrier. Okay? So, practice problem. Hemophilia is also actually known as a disease of kings because it is, you can actually Google this and watch the descent of hemophilia, the line of descent in the royal lineage, because in Europe they used to believe that you had to marry your sister and have kids with your family in order to keep that bloodline small, and that led to a whole bunch of genetic disorders and problems within the royal family. One of them being hemophilia. So that is why it's also known as the disease of kings. Incest. Yeah, fun topic. So, hemophilia is a recessive sex-linked disorder that inhibits blood clotting. So we have a normal blood clotting person, so they're going to have an X and a big H. We have poor blood clotting, which is X little h. And then we have a Y chromosome, which does not have the gene present for blood clotting on it. Okay, now, here is where we're going to find out what we're crossing. So a man who does not have hemophilia, okay, does not have, and he's a man, and a woman who is a carrier for hemophilia, okay, she is a carrier, are going to have a daughter and want to know the chances of her getting hemophilia. So remember, we're looking at the daughter specifically now. So, a man who does not have hemophilia, that immediately tells us a Y needs to be present. It also tells us that it's going to be big X, H, capital H, not a lowercase h. Why? Because he is normal, and if he is normal, he cannot have the little h for blood clotting. Okay, Now it tells us the woman whom he is with is going to be a carrier. So that means that she has a big H and a little h. Okay. Now, when we do the cross, okay, so after doing the cross, we can see one individual that will have hemophilia. We find one individual who will be a carrier for hemophilia. And then the other two individuals are going to be totally okay. They won't be a carrier. They will just be normal blood type. Okay, so the genotypes here, we're going to have X big H, X big H. We're going to have X big H Y, X big H, X little h, and then X little h Y. So our phenotypes are going to be female, normal, male, normal, female carrier, and then a male hemophilia. So the genotypic ratio, 1 to 1 to 1 to 1. The phenotypic ratio, 1 to 1 to 1 to 1. So there's only 25% chance of getting a normal female. There's a 25% chance of getting a normal male. There's a 25% chance of getting a female carrier. And then there's a 25% chance of getting a male who has hemophilia. And the question is asking us, are going to have a daughter and want to know the chances of her getting hemophilia. So there's a 0% chance that this couple's daughter will get hemophilia. However, there is a 25% chance that their son would. There's also a 25% chance that their son would not get hemophilia. So, kind of playing with fire when it comes to a lot of these sex-linked genetic disorders. In that way, especially when you have a female carrier. You'll either be born normal as a male or not. And then the female will either be a carrier or not. If only the mother is a carrier. Okay? So, forgot to put this in up top, but the father was going to be normal. So that was X big H and Y. And then the mother was going to be a carrier. So that's an X big H and an X little h. Okay? So hopefully that wasn't too confusing. If you guys have any questions, email, reach out in any way that you feel comfortable. And just remember to always ask questions when you're confused. Doesn't make you any less intelligent or anything like that. So please, you guys, reach out if you have any questions with this. Remember, you do have a quiz. Your quiz is going to be Monday, March 1st. Okay? And then I know I have one slide left. this slide is for your information only. This is not something you'll be tested on. This is just something that is actually really cool and just explains a little bit more how the X chromosome works in females, since they have an extra one, essentially, and something that we don't see in males. Okay, so you guys have yourselves a wonderful day, and I hope to see you all soon.